relatively long topic. Even in our full normal session, I couldn't complete it. Let me just split it. Let us do 2/3 today and leave 1/3 next time. All right. And before I start, last sentence about midterm. For the midterm, the coverage stops at our content of homework assignment number 1. Okay, the coverage just the end of the homework assignment number 1. All right, so we will not do more than that. The remaining part I will put in the final. Okay, so if you want to know which part you need to prepare, just look at the questions in homework assignment number 1. All right, okay, so let me start this Quicksort now. All right. Okay, all right, all right, part F, Quicksort. First, let me give you some brief introduction to Quicksort. Why we need to learn another new sorting algorithm. Let me go through the sorting algorithms we have learned so far. All right, Selection sort, bubble sort, insertion sort, merge sort. Now, number 5, Quicksort. After that, we will have number 6, heap sort. All right. Number 7, counting sort. So for this course, we will learn total 7 sorting algorithms. All right. So this is number 5. So the first question, the background, why we need to learn this many. I explained a little bit before, so why we need to solve the same problem multiple times. At that time, I gave you the reason, because we want to learn the thinking methods. This basic fundamental computing problem, sorting problem, we have many different thinking methods. And this one carries all those thinking methods. All right. But other than that, there is some other reasons. All right. Because for different sorting algorithm, our focus could be different. Our focus, or we can say in this way, the advantages and the disadvantages could be different. All right, all right, so here, before I talk about this, you can look at the title of this one, emphasize overall performance. We can recall a few of the advantages of our previous sorting algorithms. Selection, bubble, I do not talk about, because those two are very slow. So usually we do not use those two. We only use those two sorting algorithms for education purpose. All right, selection sort, bubble sort, we use them for education purpose. In the real world applications, we won't use them. All right, Then, insertion sort, it's an advantage. It's, biggest advantage. It performs really well for almost sorted data. If the data is almost sorted, then insertion sort is the best. Okay, yeah, that's it. Its biggest advantage. For merge sort, it performs really well for the worst case. The worst case, yeah. So its focus is at the worst case. It has the best worst case performance. That's its biggest advantage. Yeah. All right. Now this Quicksort, it has near best overall performance. Yep. We can, overall performance, it is the best among all those sorting algorithm we have learned so far. Overall performance. It may not have the best worst case performance. It may not have best case performance, but its overall performance is the best. You can see this property also important, right? In the real world, if you want to get the best overall performance, then you should use this Quicksort. Okay, that's the reason people give it this name, Quicksort. Why this one can be called Quicksort, right? Other sorting algorithm cannot be called Quicksort. There is some reason. The reason is it performs the best for the overall situation. All right, yeah. So let's look at the idea behind it. Yeah. This is our original sorting problem. Yeah. Number 4. Yeah. All right. We use the divide and conquer approach, but we do it differently here. Yeah. This part, because remember when we do the insertion sort, merge sort, we also use divide and conquer, right? But the ways we do the divide and conquer are quite different. Here, we will take a different view for the divide and conquer. Okay. All right. So let's look at what kind of view change we make here, we take here. All right. The goal, make the overall performance as fast as possible. Yeah. So that's our design goal. Design of the sorting algorithm, that goal. Okay. All right. Yeah. We can tolerate poor worst case performance. Yeah. For this algorithm, we do not require it has very good worst case performance. We do not require that. Okay, we can tolerate. Here, the tolerate, it means actually its worst case performance is not very good. Yeah. Let me say big theta of n squared. Okay. Big theta of n squared. That's not very good. Okay. Similar to selection sort, bubble sort, insertion sort, but not as good as the merge sort. Merge sort, n log n. Its worst case is n log n. Okay, yeah, much better than this one. Yeah. All right, but if we want to compare the overall performance, this one is better than the merge sort. Okay, yeah. Number 3, the probability for the worst case is very low. Yeah, so that's the reason we can tolerate. Okay, the probability is very low. Yeah. Otherwise, if the probability is pretty high, we cannot tolerate, right? Yeah, because it will impact the overall performance. The overall performance would be brought down by this relatively high probability worst case efficiency. All right. Yeah. All right. So that's the, our initial consideration. Yeah. Next, we want to do implementation. we want to make it happen. All right, make these three things in our design. We want to make it. All right, so next, let's look at how do we change the view on divide and conquer. Okay. All right. Here we use a different view from that of merge sort. So let us do some comparison. In the merge sort, how do we do the divide and conquer? Here we may like to do the opposite way, opposite to the way we do in the merge sort. Yeah. So let us do some comparison here. In this chart, let me compare side by side, regarding divide and conquer. Yeah. First, we know when we apply divide and conquer approach, basically we use 3 steps. The first step, divide step. Okay, you need to split the original array into 2 subarrays. How to split? There are many different ways. Okay, yeah. After that, second step, conquer. How to do conquer? Typically, we just call recursion. Yep. Our algorithms will be recursive algorithms. When we apply recursion, we take care of that conquer step, right? That means we do not need to do anything special here. Just routine recursion calling, then we can make this conquer step. All right. Number 3, after that, you need to combine 2 subarrays. So there is a combine step. Yeah. For these 3 steps, in the merge sort, the divide step is very easy. Pretty trivial, right? We split the given array right in the middle. So easy, nothing special. That's the reason the divide cost is big theta of 1. Constant cost. All right, yeah. Now the new idea we want to do differently, right? Differently, yeah. So we can spend a little more at divide step. Yeah. So we can allow big theta of k. So here, why I use k? The reason is this k means the size of current array, right? Yeah. Size of the current array. Because our array size is not fixed. When we do recursion, our current data size is not fixed. So we use that parameter k represent the current data size. Okay. And then the combine step, we want to make the combine step as easy as possible. Big theta of 1, almost do nothing. Big theta of 1 means, the minimum operations we want to do in this step. Yeah, because here you can see these two steps pretty much trade off. Yeah. You cannot do both steps very fast. That's impossible. All right. If you want to do step one with low cost, then you have to spend more cost in step 3. Yeah. You cannot make step 1, step 3, both big theta of 1. It's impossible. You have to do some work, right? Think about it. You have to distribute your work somewhere, right? Yeah. If you make both steps, step 1, step 3, big theta of 1, you almost do not do any work, right? That's not realistic. Yeah. Let's say that's probably someone's dream, but not realistic. Yeah. To be more realistic, we have to distribute our workload. Here is the workload. You can see for the new method, the workload is here. Our main workload is at step 1, not at step 3. Step 3, we do minimum. Okay? Yeah. Comparing with the merge sort, the typical workload is at a combined step. Merge step, right? The workload. That's the reason we call merge sort, right? Why we call this method merge sort. Yeah, you can see the main workload is at the merge step. All right, yeah. All right. Next. So when we look at from the high level, now you can see the main difference of these two algorithms, right? Yeah. When we make our design at the beginning, we take two different approaches, two different paths. Okay, the merge sort path, quicksort path, two different paths. So then implementations will be quite different. Yeah. All right. Yeah. So next we need to look at the implementation details. Yeah. How to make combined step easy? Let's start from there, because combined step, big theta of 1. All right. So our goal. Yeah. So let me write here. Yeah. Our goal, big theta of 1. Okay. Doing something very little, yeah, but you need to do something, but small amount of work. Okay, small amount of work. But the question's how to make that happen. How to make that happen? Combined step. Yeah. Almost doing nothing. How can that be possible? Yeah. So let's look at the possibility, how to make that happen. Yeah. Almost do nothing in the combined step. All right. You have two sorted arrays, because after the conquer step, those two subarrays, we can assume they are sorted. Yeah. Array A, array B, these two subarrays, we can assume they are sorted. Now we combine two sorted arrays and we get a overall sorted big array immediately. How can that happen, right? Yeah. So before the conquer, these two subarrays are not sorted, right? But the conquer step, we just apply recursion, right? So we don't worry about the conquer step. After recursion, these two subarrays are sorted, all right? Yeah. So, okay. After sorted. So we can assume they are sorted before we combine them. Yeah. All right. The next question. Yeah. After we join these two sorted subarrays, we immediately get an overall sorted array. To make this possible, we need to put some condition there. We have to have some special condition on our data. Yeah, that condition is important. Yeah. All right. Yeah. So we just put one after another. The whole array is automatically sorted under some condition. Yeah. Under some condition. If there is no such condition, this won't happen. Okay, this probably won't be there. So that condition is important. Yeah. So we want to find that condition. Yeah. All right. Okay. So the next step, So let's see that important condition. Okay, all right. Think about the order information. If we need to consider some special order information on two subarrays of our data. Okay, all right. So here the condition is very simple as this. Yeah. The value of each element in a subarray should be smaller, less than or equal to any element in B subarray. The value of any element in B subarray. Yeah. Here we use arbitrary index I in the left subarray and arbitrary index J in the right subarray. Yeah. So you can imagine this. Yeah. You can pick any element in left subarray and any element in right subarray, you always have this inequality. Okay? Or you can think in another way, the maximum of the left subarray is smaller or equal to the minimum of the right subarray. How about that? The maximum of the left subarray cannot be greater than the minimum of the right subarray. How about that? Okay. With this condition, then when you combine, you join these two subarrays. If the left subarray is sorted and the right subarray is sorted, then you join them together, you get a whole overall array sorted immediately without any extra work. Think about that, all right? So then this condition, it looks like pretty natural, all right? Yeah, okay. Now we know in our divide step, we need this condition. This condition comes from the divide step. At divide step, you need to enforce this condition, okay? Yeah, but the question is, how can you make it work in the divide step? Then we need to do a lot of work. That's the reason our most workload is distributed at the divide step, right? Because we need to make this condition work. We need to do a lot of work to make it happen. Yeah. All right. So next, we need to look at the divide step. That's the key step of this algorithm. Okay. All right. The most important step, divide step. Yeah. So in the divide step, if we do some appropriate arrangement, yeah, so do things right, then we can enjoy some easy, fast combine step. Okay, yeah, so that's the main point. Yeah. All right, the requirement. What kind of condition we need to ensure at the divide step? Yeah. All right, so basically what we need to do, split the array into two subarrays, A subarray and a B subarray, such that A of I less than equal to B of J. That's what we need to do at the divide step. Okay, yeah. So it is pretty clear what we need to do at the divide step. The next question, how to make it happen? How to fill in the details to get this requirement. All right, so that's our next discussion. All right, yeah. Yeah, so here I put this remark here. Yeah. In each individual subarray, we do not require the individual subarray sorted. Yeah, because that's not necessary. A subarray is not necessarily sorted. B subarray is not necessarily sorted before conquer step. After divide step, before the conquer step, we do not require each individual subarray sorted. Only after conquer step, we call recursion, then each individual subarray is sorted. Yeah, so that part is in the conquer step, okay? But in divide step, we do not require that. So that would reduce our workload. If we require individual subarray sorted, then you need to do too much work in the divide step. That won't be good. Yeah, that won't be good. All right. Yeah. So here, yeah, you need to understand, we don't want to put too much workload in the divide step. All right. All right. Next, F.2, partitioning of quicksort. This is the key operation of the quicksort, partitioning. That's the divide step. Okay. Yeah. All right. So let me describe the partitioning step, the details. All right. Implement the divide step. We need to fill in the implementation details, but we need to follow some logic. We need to, explore the details. Okay, yeah. Look at this diagram. Yeah. So that's our original array. We want to split it into two subarrays, A subarray and a B subarray. But we cannot split somewhere, yeah, because if you split somewhere in the middle, you won't have our inequality condition. You won't have that. Okay, yeah. So you have to do some arrangement, moving elements from left to right, from right to left. You have to do some work. Elements moving work. You have to do, yeah, necessary elements moving work. The question, how to move the elements to make this condition hold, that's the main work we need to do in this step. Yeah. All right, so let's look at that part. How do we move elements around? All right, yeah. Here, to get that part, let's look at uncertainty. There is some uncertainty regarding the sizes. How large is the left subarray and how large is the right subarray? How many elements in the left subarray? How many elements at the right subarray? Nobody knows that. Nobody knows that, right? So that's the uncertainty. Okay, yeah, something to be determined later. Okay, yeah. All right, how to make it certain? Yes, we need to do some special work here. Yeah, here the idea, we need some special element to separate. How to separate two subarray? Yeah. We cannot use data sizes to separate. It's uncertain. How can we use the data size to separate, right? So we cannot use that data size information, but here we want to use some other information. Here we need to find a special element. That element can be used to separate two subarrays. Okay. Yeah. Question: how to choose some special element? That element plays the role of a separator. Separator of two. So look at that element is very special between two subarrays. In the middle, between two subarrays, and its role is the separator of two subarrays. How about that? How about that view? That new view, separator view. Okay, yeah, all right. So the key property, that separator must be in place. Okay, that separator element must be in place. Okay, yeah, that property is important. Yeah, the separator element is in its right position, location of the finally sorted array. Then it can be used as a separator, right? Yeah, so you can see, yeah, we need that, okay? So now we need to determine the boundary of two subarrays. Boundary, yeah, the separator, it's the boundary of two subarrays, okay? Yeah, how to determine that element. All right, so let's look at this new diagram. This new diagram, yeah, so we interpret, so here we have this special element in between two subarrays, P element, yeah, we call it pivot element. Yeah, that separator element that is in place, we give it a special name, special concept, because its role is so important. Its role is critical. So we would like to give it a special term for it. Pivot element. Pivot. Okay? Yeah. This pivot is in place. Okay? Then we can look at the left subarray of this pivot element and right subarray of this pivot element. Yeah. Its left subarray has this property. Okay? A of I less than or equal to P value. A of I value less than or equal to the P value. Okay? The right subarray, the P value is less than or equal to B of J value. Look at that. That's the important property of this pivot element. How to do that? That's our next question. Here we just want to make it clear we need to do this. This is the result of our partitioning step. Okay? Or you can say this is the goal of our partitioning step. After we complete the partitioning step, we want to get this state for our data. This is the state of our data after the partitioning step. Okay, all right, yeah. So let's move to the next slide. Now we need to make this device step satisfy our goal, our target. Yeah, all right. Which element is used as the pivot? Next question. Yeah. We need to select the pivot element, but which one is the best one for the pivot? So let's look at this question next. Okay, all right. The answer is any element has an equal role in the array. Yeah, because when the data is given, you have no idea on the values for any element, right? Which one is larger, which one is smaller? You have no information for it. Okay, under that condition, which one should be the pivot? You have no information at all, right? You have no information at all. then every element has the equal chance to be the pivot. How about that? Each of the n elements has the equal chance to be the pivot. Think about that, this statement. Equal chance. Okay, yeah, that's fair. That's fair. Yeah, without any information, that's fair. All right. Yeah. Okay. Yeah. No reason to favor any particular element, right? Yes. If you favors, let's say, the third element, do you have any special reason to favor the third element in the array? No reason, right? Yeah. So you can just pick a random element to be the pivot, right? Equal chance, the random element. You can use any element as the pivot. Equal chance, right? Yeah. That's the first understanding. Second, yeah, we need to do a little more than this equal chance. After this equal chance, we need to consider the convenience factor, right? That equal chance is regarding the values. When you look at the values regarding, regarding the element values, our conclusion is equal chance for any element in the array. But that's not enough. There is another factor we need to consider, the convenience factor. How convenient it is, right? For different elements in the array, we may have different convenience thing. Convenience thing, what's that? Yeah, let me explain that convenience factor. Okay, all right. Yeah, so that's our, first round understanding. Our second round, we want to focus on the convenience factor. All right. Position-wise, element at which position is the most convenient? Convenience factor. Yep. So let's look at this issue next. I need to draw a diagram to show you, this consideration. Also very important. Yeah. All right. Here, let me use these boxes, sequence of boxes representing the locations for all the elements in the array. Yeah. Now, we need to consider for different locations, the work we need to do could be different. Some locations could be better than other locations. Think about that. Yeah. The locations, they do not have equal chance, right? Locations, because they're so different. You cannot say with respect to the locations, each one has the equal chance. That's not correct. Yeah. Let's say for different locations, the importance is different. Think about that. Okay. Yeah. All right. Let's look at one location in the middle. Yeah. Think about if we choose one location in the middle for our pivot element, how much work we need to do here. Okay. Yeah. Look at that. Yeah. Because if you choose a random element in the middle, usually it's not in place, right? How can you choose one element in the middle and it is in place? Nobody can do that, right? Yeah. To be more realistic, you should assume this element is not in place. Okay? So it is not in place, then how do you make it in place? Think about that. How do you make this element in place? Think about that, right? Yeah, because when you move elements from left to right and from right to left, this element, this position, this location will be the roadblock, right? Think about when you move elements from left to right and from right to left, this element will be the roadblock. You need to do a lot of work to get around this roadblock. Think about that picture, okay? So that's not convenient, right? Yeah, because you have to move elements around, from left to right, right to left, in order to get this destination state, this state, okay? Yeah. So that roadblock, that means that position is not convenient, not friendly for our operation. We need to find friendly locations, convenient locations, okay? Yeah, all right, yeah, so we cannot take that roadblock type locations. We need to find non-roadblock type locations. Yeah. What are the non-roadblock type locations? Yeah. So that's the question. Yeah. It won't block any move of the elements. It won't block. Okay. Yeah. Only two special locations, the first one and the last one. Think about that. If you use the first element as the pivot location, then when you move the remaining elements, here and there, you do not need to touch this element, right? No roadblock thing you need to do. Similarly, for the last element, if you use that as the pivot element, when you move other elements here and there, you do not need to touch this pivot element, right? You do not need to do any work regarding this pivot element, right? Yeah, so these two locations are the most convenient locations for our pivot element. So it's not an equal chance issue, right? Yeah. If we look at the position factor, so, these two locations are very special, very friendly. So we should choose one of these two locations for as our temporary pivot location. Temporary pivot location. Yeah. Think about this word temporary. Why temporary? Because this location not in place, right? We know this, if we use as pivot location not in place, temporarily, not in place temporarily, okay? Yeah, but at the end, we will put it in place, yeah, without any problem. Yeah. At the end, we will make it in place. But, before the end of the partitioning, yeah, it's not necessary in place, okay? All right. So this analysis, for this analysis, now, I hope you have some good understanding of the pictures. Yeah. So I spent a lot of time. Yeah. I spent about 40 minutes, quite some time, to give you the background story of this sorting algorithm. Okay. All right. Next, we have just about 10 minutes. Let's see how far we can go here. Now, to make things a little clear, yeah, here, let us use the last element as the pivot. Although you can use the first, the same procedure. Yeah. In our textbook, it uses the first element as the pivot. Yeah. All right. Yeah. So not much difference. Yeah. All right. So in our discussion, let me just use the last element as the pivot. Okay. All right. Then we should get A subarray and a B subarray, and the elements in those two subarrays are arranged like this. Okay, yeah. And we require all the values in A subarray should be less than or equal to P, and all the element values in B subarray should be greater or equal to P. Okay, so that's the end state of our part. Oh, yeah, let me say this way. Yeah, that is the, end state. Actually, yeah, because after this step, we need to put the pivot element in place. There is another small step we need to do to complete the partitioning. Yeah. So here you can see, just before that in place step. Yeah. This is the state of the partitioning before the last in place step. Yeah. We can say in this way precisely. Yeah. Yeah. All right. So next, F.3 implementation in partitioning. Yeah. Yeah. Let me see how far I can go. Yeah. All right. I only have 7 minutes. Yeah. Let's say 6 minutes. Yeah. 7 already. Yeah. To be safe, let's say 6 minutes. Yeah. Straightforward implementation. Yeah, we can do straightforward implementation. Yeah. All right. All right. Use 2 auxiliary arrays. Then we can do straightforward. That's easy. Yeah. But that may not be the best. Later we will improve. Yeah. Straightforward implementation. Let us use 2 auxiliary arrays. That means we need to use extra space, extra amount of space. That's resource. That's extra resource. If we can save the extra resource, that's really good, very important. Yeah. But before we find our final solution, let's take some relatively easy way to find a temporary solution first. All right. When we scan the array, we like to make arrangements like this. Yeah. We have a left subarray, right subarray. The space here, extra space. Okay, yeah. Here we consider extra space. Okay, yeah. All right, so left subarray, right subarray. Okay. All right. Then you can imagine we just scan when we take each element in the original array, we compare it with P. If it satisfies the condition A of I less than or equal to P, we place it in the left auxiliary subarray. All right. If we find that A of I is greater than P, then we place it in the right auxiliary subarray. How about that? That arrangement is simple, right? Pretty simple, straightforward. And we can split the original array into 2 subarrays immediately. The question is, we use extra space. That's bad. We waste a lot of space. That's not a good solution. Right? We should avoid using this much extra space. We should avoid this much extra space. Okay? Yeah. In other words, we should only manipulate the elements in our original array. Okay? Or we should use we can use extra space, but the minimum extra space. Minimum, not this much. Okay? This way, we use too much extra space. Okay, so that's the reason it's not good. So if we just use 1, 2, 3, small number of extra locations to store temporary variables, that's fine. Okay, that's a small amount of extra space. We can take it. But here, we need to pay too much cost for the extra space. That's not a good solution. So we should avoid it. Yeah. So our next step, we need to improve. We need to get the same thing. That means we need to get a split like this without using this much extra space. Right? Yeah. So you will see, yeah. Although this way, easy to understand. Yeah. After you get two subarrays, you just copy them back. Okay, copy back. But because you use the extra space, that will impact the final performance. That would make the final performance slower. If you use more space, sooner or later, you will make your algorithm implementation slower. That's not good. Okay, we should avoid it. Yeah. All right. The next question. Yeah. So acceptable after my long analysis, we know it's not acceptable, right? So we need to reduce amount of space used. Yeah. The question, how to reduce, how to eliminate those auxiliary arrays. Yeah. Let me talk about that part next time. Okay, so next time we will do that part. Then we will complete the partitioning. Then we're almost there. You know, for the quicksort, the main workload is at the partitioning. After the partitioning, we almost complete it. Okay, yeah. So that's the, you know, good thing about the quicksort. Okay, so next we will complete this partitioning step by eliminating the auxiliary arrays. Then we will do some analysis work and do some examples.